So here are the rules you can use to draw the level structure of one chemical compound. So first, because when we talk about the bonding in chemical compounds, we focus only on the valence electron. In one atom, you have core electron depleted inside, being very close to the nucleus, so have a strong binding with nucleus, so not very useful, not active. And we have a valence electron who stand in the outer layer of the atom, where the electron can be removed to make cation, where the atom can receive new electron to make anion, or the electron can be shared. So when you want to describe the chemical structure and the chemical bonding, you pay attention in the valence electron. So in one compound, you have several atoms. First, you need to calculate the total number of valence electrons of all the atoms you have in the compound. And then you write down the symbol of the atom. You put the atom with less electronegativity in the center, and the atom with higher electronegativity surround this central atom. Then you complete the octet around all the atom bond to the central atom. So you complete the octet, that means to make the atom surround, satisfy having 8 electrons first. Octet means 8. So after satisfy all the atoms surround with 8 electrons, any leftover electron you will put in the central atom. Then you look at the central atom to see whether it satisfies the octet. If it has more than 8 electrons, you need to reconsider the structure. Or it has less than 8 electrons, you need to reconsider the structure by multiplication of the chemical bond between the outer atom and the central atom. So by repeating the 5 steps, you can define the final structure of one compound. So let me take one example. If you are given the compound BCl3. So first, here you have one atom phosphorus and 3 chlorine atoms. So the phosphor have 5 valence electrons and 8 chloride have 7 electrons. So in total, you have 26 electrons. And you know that phosphorus have lower electronegativity compared with the chlorine. So you put first phosphorus in the center and you put 3 chlorine surround. You first link 8 chlorine to the central atom, which is phosphorus, by one single bond. And then you complete the octet for the chlorine. So you can see here, 8 chlorine have 8 electrons. So now in total, you have already used 24 electrons. And in this compound, in total, we have 26 valence electrons. That means it still left 2 electrons, and then you put the 2 leftover electrons in the phosphorus at the central atom. Now, you look for the number of electrons around phosphorus. The chlorine, you have 2 here. So this phosphorus, you have already 8 electrons. So the phosphorus atom satisfy or also the octet rule. So this structure is correct, and then you can stop here. Okay. Now, because to do this kind of drawing Lewis structure, I invite you guys remember 5 steps, and then practice more and more. You practice faster, you can complete the drawing of a Lewis structure. So I invite you guys to work later on some exam. But here, one question. You know the Lewis structure of BCl3. So based on this Lewis structure, can you predict whether BCl3 is a Lewis acid or a Lewis base? Anyone can comment whether BCl3 is an acid or a Lewis base? So actually we know that by definition, the Lewis acid compound that can accept 1 electron. A Lewis base, this can give 1 electron. Okay. So here you can see that in the phosphorus central atom, you have phosphorus with a pair of non-bonding electron. So it can give the electron to another compound. So that's why this PCl3 working like a Lewis base. So if you put PCl3 react with nickel 2 plus, you can have this compound. This is a typical acid-base reaction between BCl3, a Lewis base, and nickel 2 plus, a Lewis acid. Okay?
Okay, teacher.
So I invite you guys to revise a little bit the theory of acid-base. You have in general, you have 3 different definition of acid-base. You have a process acid-base definition, you have Arrhenius acid-base definition, and you have Lewis acid-base definition. Okay? Now, let's be practical a little bit. Can you draw the Lewis structure of molecule NO2? You can have 2 minutes to finish this practice exercise. Can you? Please take a paper and try to draw the Lewis structure of molecule NO2. Phạm Quốc Bảo, have you done? Bảo?
No, I don't.
Can you try to draw your structure? Can you try to draw your structure on my slide? Can you?
No.
No. Nguyễn Ngọc Đại.
Yes, I'm here.
Yes. Can you try to solve your structure?
Sorry, I can't. I don't
Why?
know how to solve it.
But we are trying. We just finished describing 5 steps how to draw the Lewis structure. Can you try? By following 5 steps that I described. Anyone can solve your structure? So let's practice 5 steps, right? First, you define the total number of the valence electron. Okay, so how can you share your structure? I can stop sharing now and you share your structure. Okay, maybe NO2,
please,
right?
please keep it on.
Right before, I don't see where it's annotated, but I can see it now.
Okay, let's say.
Okay, can you share the?
Okay. Hold on. Okay. Can you try? How?
Yeah, I will try. Oh, okay.
Okay.
Yes, here
Okay.
is.
But then, how about the number of electrons surround promise? In this one, it will have from with 4, 8, 10, and it will have 12 electron. Is it correct? For this promise. It will be too much, right? So let's we do step by step. Yeah, me, please. Can you comment?
So please continue. I don't know how to explain it.
Okay. Then how can you come out with this structure?
Because I use how to say it? There are 8 electrons around the oxygen, and
oxygen it will have a more 8 electron here in this structure. Here it will have 6 and 10 electron. Yeah. This electron, you will have 8 electron. Oxygen. Okay.
Ah.
Let's we go first on the
Yeah.
nitrogen. NO2.
That was mistake.
No, never mind. It can happen. So let's say the nitrogen, you can have 5 electrons, right? Oxygen, you have 7 electrons. So in total, this molecule, you will have 5 plus 2 times 7 equal to electron. Okay. And you know that the nitrogen have lower electronegativity compared with oxygen. So first you put nitrogen, and then you put surround oxygen. And you try to make by a single bond first. Okay? And you know that one single bond equal to 2 electrons. Now, the next step, you try to satisfy the octet electron for oxygen. Here you have a 2 already. Then you put 2, 2, and 2. So this one, you will have 8 electrons. You do the same thing with oxygen, the second one, and then here you will have 8 electrons as well. So in total, you have already 16 electrons. Okay? Sorry, I make a mistake, terrible one. Oxygen have a 6 electron. Okay? So you have 17. Sorry for that. Okay? And then you have 16, so here you have 1 electron more, because in total you have 17. Okay? So you have 1 more nitrogen here. And if you look in the number of electrons in the nitrogen, you will have 2 plus 2 plus 1. So in total, you have only 5 electrons in the nitrogen. It's very small compared with electrons you should satisfy. So you can try a second solution. You put nitrogen in center. You put oxygen here. You put 1 double bond. And when you put the double bond, then you have oxygen with 4 electrons. So in total, it has 8 electrons here. You do the same thing for oxygen here. So this one, you have 8 electrons as well. So here now, still you need put 1 electron remain here because it has total 17. Now you calculate again the number of electrons surround nitrogen. Here you have 4 electrons, right? 2 pair of electrons here and 1 pair of electrons here. So now the nitrogen, it will have 4 plus 2 plus 1 equal to 7 electrons. It's not yet satisfied the octet rule because it cannot. It have an odd number of electrons. We will see later when you have an odd number like this, then you cannot satisfy the octet rule. But it's closer to the 8 electron. So this structure is more likely than this one. Okay? So the correct answer will be nitrogen like this. Okay? Understand? Is it
Teacher.
clear to you guys?
Teacher,
Yeah?
can you talk again about the double bond? I still don't really get it.
Okay. Now, hold on 1 minute. You agree with me that first, by 5 steps, first, I try to use the single bond between oxygen and nitrogen, right? And in the case I use single bond like this, the number of electrons in the nitrogen will be 5. Is it correct? You can calculate to have 5, 2,
Yes.
2, and 1. It's quite far from 8 electrons. And you understand that by the octet rule, the compound need to satisfy 8 electrons. Of course,
Yes.
when you have an odd number, you cannot perfectly satisfy the octet rule, but you can try to have closer value to 8. So 5 is quite far from 8. So you try another solution. You put nitrogen, oxygen in the center. And instead of making one single bond, you make a double bond here. And one single bond here. Remember? So here a double bond, you have already 4 electrons, right? And a single bond, you have 2 electrons. Because now you need to satisfy the octet electron of X oxygen. Here you have 2 electrons, so you put 6 more electrons around. So this oxygen will have 8 electrons. This oxygen, the second one, you have already 4 electrons from the double bond. So you put 4 more. So this guy will have 8 electrons. Well, the total you have a 17 electrons. So you will have 1 electron left in the nitrogen. Now you do the calculation of the number of electrons in the nitrogen. You have 4 electrons here and 2 electrons in the single bond and 1 free electron. So in total, this nitrogen, you will have 4 plus 2 plus 1 equal to 7 electrons. 7 electrons is not yet 8 electrons, but it gets closer to 8 than 5. Is it correct?
Yes.
Can you get it now?
Yeah, yes, I think that I will get it.
So basically,
Yeah.
you need to satisfy 8 electrons. But when you have odd number, you cannot have whatever you do, you cannot reach 8 electrons. It belongs to an exception case. So what you can try to do is try to make the number of electrons in the central atom closer to the number 8. So here you have 2 possibilities. You have NO2 with a single bond. The nitrogen in the center will have only 5 electrons, so quite far from 8. If you have 1 double bond and 1 single bond, you have a central atom nitrogen with 7 electrons, so it gets closer to 8 than 5. So the structure number 2 with a double bond and 1 single bond is more likely compared with the NO2 with 2 single bond. Is it okay?
Yes, I get it. Thank you.
Okay. So now if you pick up the structure that me mentioned, BCl, BO3 minus 1, so bromide, you have 7 electrons. And oxygen, you have 6 electrons. So BO3 minus, that means you have 7 plus 3 times 6 plus 1. So it's equal to 8 plus 26 electrons. Is it correct? So now you put the lower negativity atom, bromide, in the center. You put oxygen around like this. First, you try with a single bond. Okay? And you try to satisfy 8 electrons for X oxygen. Okay? So now in total, it will have 8, and then 8 electrons. So in total, you have 3 times 8 equal to 24 electrons already. So it remains, compared with 26, it remains 2 electrons you put in the bromide. And when you put 2 electrons in the bromide, you see that the brom will have 2 electrons in the single bond, 2 electrons in the single bond, and 2 electrons in the single bond, plus 2 free electrons, non-bonded. So you have 8 electrons for the bromide as well. So the correct answer would be this structure. You put 1 negative charge outside, like this one. Is it okay?
Excuse me, teacher. I want to ask a question.
Yeah, please.
In the brom bacteria, I think that if you draw this structure like this, so
Mm.
the form charge of bromide will be +2, and all around the oxygen will have the formal charge will be -1. So I think
Yeah.
that this will have a lot of like charge.
Yeah.
And
Thank you.
when
Yes.
I remember well, when I study in high school, we usually prevent from writing the structure having a lot of formal charge like this.
Yes.
So
Yes.
I'm really wonder why. Yeah.
Yes.
Can you
Okay.
explain?
Thank you, Tao. So basically, we have not yet talked about the formal drugs later in the next slide. Okay. So now we try to use the 5 step to practice how we use the 5 steps to draw the Lewis structure. And then in the case when we have several potential Lewis structure, we need to consider which one is more likely. Okay. And then to make decision which one is more likely between my structure I draw here and your structure, we need to move in the next slide when we talk about the formal charge. Okay? Can you get what I mean? Okay. Thank you to move in advance. Okay. So you see that if you pick up the 5 steps that I provide, you can come out with my structure. Okay. Then another like Thảo also, don't Thảo, you are Thảo Mi or Thảo?
It's Thảo Mi.
Okay, Thảo Mi. So Thảo Mi propose another structure. And then you will see that other structure can be also likely, that means can be also acceptable if all the atoms surround. Let's say you can put this kind of structure like bromide, oxygen like this. Huh? Sorry. And then you will have also another potential structure like this one. Okay. Then you have this one. Okay. Okay. So you mentioned about this structure, right? Okay.
Yeah.
So which one is more likely? Then we need to look first in this structure is the can be better if you want. In this structure, all the bromides and oxygen satisfy the octet electron. Okay. Whether for this case you have oxygen 8 electron, oxygen electron 8 electron, and this oxygen 8 electron as well. But the prom in the center, it will get much higher than 8, right? So you have 4 plus 4, so you will have in total 12 electrons. Is it correct?
No.
Why?
Because it can have 12 electrons around the bromide.
But by this structure, you will have this one.
Yeah.
If you draw the structure like this, you will have this one. Okay?
Yeah.
So basically, you first follow the 5 steps I used to describe, where you try to satisfy each atom in the structure with 8 electrons. And in the case, you can have more than 2 structure which have the same possibility to satisfy all the atom with electron, then we need to consider which one is more likely by using the formal charge. But if one structure can provide atom with more than 8 electrons, then we need to consider a little bit later. The case of the case of bromide is quite sensitive if you want, because bromide is in the so the fluoride is second row, chloride is third row, and bromide is in the fourth row. Okay, so the bromide has the d orbital. So because of that, the bromide can accept more than 8 electrons. You get what I mean? So the octet rule, remember that the octet rule is acceptable and strictly obey for the first and the second row element, where you have the orbital s and p. Because you have 1s and 3p, so the maximum number of electron, valence electron you can accept is 8 electrons. So the octet rule is applicable for the element. But when you move to the third row element, because you start to have orbital d, 3d, right? So when you have orbital d, you can have 1s, 3p, and 5d. So in that case, the maximum number of electrons can fit in the valence orbital will be 18, not 8 anymore. So the case of bromide is quite sensitive because bromide is in the fourth row. You get what I mean, Tommy?
Yes.
Okay. Okay. So first, recall 5 steps. First, you do the total, you calculate the total number of valence electrons in the molecule or ion that you have. Second, you put the atom with the lower electronegativity in the center, and you put all the atom remain surround. You try first to link the surround atom with the central atom through a single bond, and each single bond equal to 2 electrons for sure. And then you try to satisfy the surround atom with 8 electrons. Any electron left after that, you will put in the central atom. And then you consider whether the central atom have 8 electrons, obey the octet or not. If it's not, then you can change the structure by trying the bonding between the surround atom and the central atom by a double bond. By repeating like that, it will find out more likely Lewis structure. Okay? Now, if you have more than one way to draw Lewis structure that Tommy mentioned, how can we decide which one is correct? And if we want to decide which one is correct, we must use the concept of formal charge. So for example, the 3 structures you can see in this slide, all of them satisfy the octet rule for the atom. Okay, so which one is more likely? Which one how we can decide which one is correct? Then we use the concept that Tommy mentioned, the formal charge. So how we can define the formal charge? So the formal charge is the charge of the atom could have if all the atom in the molecule have the same electronegativity. That means you consider each bonding electron pair in the molecule will share equally between its 2 atoms. What does it mean? So it means normally when you have a covalent bond, a single covalent bond, you have 2 electrons. It makes the covalent bond because the two atoms share their electron to make this covalent bond. And normally the two atoms have different electronegativity. When they have a different electronegativity, you can imagine that one atom have higher electronegativity, can have a more tendency to attract the electron. In other words, the two electrons belong to two atoms, but the guy have higher electronegativity will have a higher chance to keep the two electrons. In other words, the electron density will localize higher in the higher electronegativity atom. But now you consider that the two atoms, whatever their electronegativity, they will have the same chance to receive electron. In other words, the electron density will be equally distributed in two atoms. So in that case, you pick up a pair of electrons in the covalent bond, you say that X of you guys will take 1. So by that way, we will calculate the formal charge. So now, X atom, before involving making any chemical bond, will have a fixed, a given number of valence electrons. So after making this kind of distribution of the valence electron in the bonding, if you look at the difference between the electron is have compared with the valence electron is have before making the bonding, you would know the formal charge. Let's we look at the case of carbon nitride here. So you have a triple bond between the carbon and nitrogen. The triple bond means you have a 6 electron. Okay. So imagine that the carbon and nitrogen equally get the 6 electron. So 3 electrons will belong now to carbon and 3 electrons belong to the nitrogen. And then this carbon have 2 more electrons non-bonding. So in total now, you have the carbon with 5 aside electrons. Okay. Before making the carbon nitrogen triple bond, carbon have 4 valence electrons. But now after making this valence bond, and then making this covalent bond, the carbon have 5 electrons. So it means that it have 1 electron excess. So we say that the carbon in this case have, because 1 carbon is 1 negative charge. Oh, sorry, 1 electron is 1 negative charge. So the carbon have now 1 minus formal charge. How about nitrogen? You have 3 electrons here and you have 2 electrons non-bonding. So in total, you have 5 aside electrons. Before involving in this covalent bond, nitrogen have a 5 valence electron. So it will not change anything. The number of aside electrons equal to the number of valence electrons. So the formal charge on nitrogen will be 0. Is it clear? So now we come back to calculate the formal charge. So sorry, you guys. Actually, you know that's yesterday at university we do a quick test. We did a quick test for all the staff, PhD student and master student, and we have 2 positive cases. I grew 1 of the 2, so I am isolated in my room at home, and I feel very bad now. So during the lecturing like this, I receive quite a lot of number of messages and phone calls. So sometimes I need to answer or feel, because otherwise people will feel very you know. So never mind. But I know that it's quite difficult to cancel on B1 class because your agenda is very tight. So I try to provide a lecture, but you can feel that I don't feel very good today. But never mind. So now we first try to calculate we try to identify the formal charge on the language structure. So let's see this one, the nitrogen, it will have one belong to the nitrogen, so you have 7 electrons. Okay, here you have 3, so the carbon you have 4 electrons, and the sulfur it will have 3 plus 2 equal to 5 electrons. And you know that the number of valence electron, carbon is 4, nitrogen is 5, sulfur is 6. So here you have a nitrogen with 7 electrons. That means the formal charge on nitrogen will be 2. Carbon will be 4, so the formal charge on the carbon will be 0. Sulfur you have a 5, so the formal charge will be +1 because it like 1 electron compared with a normal electron configuration. You do the same thing for the second structure. So here you have 6 electrons. Here you have 4 electrons. And this one, you will have 2. So you have 6 electrons. So it means that this structure, it will have nitrogen with 1 minus formal charge, carbon still 0, and the sulfur, it will have 0. Here you have 5 electrons. You have 4 electrons. 6, you have 7 electrons. So the nitrogen here, you will have the formal charge 0. Carbon, you have a formal charge 0. And the sulfur, you have a formal charge 1. Okay? Now, you know the formal charge of X atom in the 3-level structure. How we choose the correct structure? We generally choose the level structure in which the atom bear formal charge closest to 0. So in the first structure, you have formal charge of -2 and +1. In the second one, you formal charge, you have a formal charge -1. And the second one, you have formal charge -1. Other atom have a formal charge 0. So by applying the first rules, we can rule out the first structure, because in the first structure, you have a formal charge -2 is far from the 0, further from 0 compared with the second one and the third one, where you have formal charge -1. So 2 potential structure will be this one. You can rule out the first structure. Then among the 2 structures, the second one and the third one, which one can be correct? Then we move to the second rules. We generally choose the language structure in which any negative charge will put on the more electron negative atom. Okay, so now you have formal charge -1, so negative charge. In the second structure is put on nitrogen. In the third one is put on the sulfur. Now we need to look at which one have more negative higher electron negativity. So if you move to this table, you will see that the nitrogen have electronegativity of 3.0 and the sulfur 2.5. So it means that it's better, it's correct if the negative one will put on the nitrogen instead of on the sulfur. So when you come back, you see that the second structure where the formal charge -1 on nitrogen is correct, because the third one, the negative charge -1 will be on the sulfur, which has lower electronegativity compared with nitrogen. Is it okay?
Okay.
Thank you. So again, to recall new lipids by applying the first rule, choose a language structure in which the atom be a formal charge closest to zero. So you have the second and the third structure can be possible. And then by moving to the second rule, we choose the language structure in which any negative charge will reside on the more electronegative atom. So here you have a nitrogen is more negative. So you put on the nitrogen. So that's why you have the second structure will be the correct one. Okay. Now we move to the next concept, resonance structure. So when you have a more, two or more possible language structure, so after deciding based on the formal charge, which one is more likely? Let's look at the case of the O3, the ozone. You can have two structure quite look like similar, like this one. Okay. Now you have O3. So let's say you put three atom oxygen A, B, and C. If you look in this structure, you remember that the double bond will be shorter than the single bond. The double bond will be stronger than the single bond. So what you can learn from this structure, you can say that the distance between of the bonding OA, OB will be shorter than the distance of the bonding OB, OC. Okay? And you can say also that the electron here, the electron density on OC will be like the oxygen in the oxygen C can have more basicity compared with oxygen A and B. So if you have the protonation, imagine that you can expect the protonation on this oxygen C more than the protonation on O, A and OB. So that means in terms of the basicity, you can expect OC higher than OA. It means that you can experimentally distinguish the three oxygen atom. More specifically, you could be able to distinguish OA and OC. But actually, in the experimentation, OA and OC are exactly identical. In terms of the chemical bonding, the bond length between OA, OB, and OB, OC are exactly identical, like this one. So you see that in the molecule O3, the bonding are exactly identical. You cannot say that the OB, OC is longer than OB, OA. So you remember that chemistry is science of experimentation. So all the theory we discover, we propose to explain experimental result. So the real motivation, the real driving force will be experimental result. So when the experimentation says that we cannot distinguish OA and OC, we have to develop the theory to explain why OA and OC are identical. So to explain, we say that the two structure 1 and 2, they are both likely, they are both coexist in the real structure of O3. And there is a kind of resonance between the two structure. Okay, so the resonance structure describes the different structure that can coexist in one chemical compound. So sorry. So I hope that I already explained. You can understand why they develop the concept of resonance structure. Of course, when you can draw more than 2 or more than equally valid Lewis structure, then you can say that these structure are resonance structure. But the behind of the proposition, why they propose the resonance structure, is because the Lewis structure that we describe till now cannot explain the experimental result. The similarity between the OA, OB, and OB, OC in the case of ozone molecule. So they need to develop the theory by using the concept of resonance structure to approach, I mean, to explain better the experimental result. Of course, in chemistry, when you have a rule, you will have exception. So when we talk about the Lewis structure and octet rule, you have 3 main type of exception. First, the odd number of electron. For the case of NO2, you see the nitrogen have the odd number 5 electrons. So anyone in this compound, you cannot satisfy the octet rule, because the total number of electrons in the nitrogen will be never 8. So in the case of NO2, it will have 1 single electron in the nitrogen when you have an odd number of electrons. And you can have a fewer than octet of the valence electron. When you have a 7, it's fewer than 8. And you can have also more than octet valence electron. For example, the case of bromide, I discussed with Tommy. So for the case of odd number NO2 and NO, you see for the case of NO2, you will have nitrogen 5 electrons. So NO will have 11 electrons, that is odd number of electrons. So of course you cannot satisfy the octet rule. Fewer than 8 electrons. Take the case of BF3. So in total you have 24 electrons, and then you have when you draw the Lewis structure, you will see that the bromide will have only 6 electrons, smaller than 8. It's also say that the Bohr does not obey the octet rule. But because of that, so BF3 can receive electron, so it acts at a Lewis axis. That's why the BF3 will react with a Lewis base like Na3 violently it's a acid base reaction to make this compound. And when you have this compound, the boron will satisfy 8 electron, so it's obey the octet rule. So like BF3 can also react with, let's say, B18 ether to make a complex detonator BF3. Okay, because it's have fewer than 8 electrons, so it reacts, it behaves like a Lewis axis. Okay, you can have a more than 8 electrons in the case of BCl5 or SF6 here. So for the case of BCl5 here, you can see that phosphorus will have 10 electrons, and the sulfur here you have 12 electrons. It's much higher. Oh, sorry, 10 electrons. You have a much higher than the 8 electron of the octet rule. The reason that I mentioned, for all the elements from the third row or fourth row, you will have a d orbital. And when you have a d orbital, the total of orbital you can have is 1s, 3b, and 5d. So the maximum number of electrons you can go is 18 electrons and no more, only 8 electrons. So for this case, you can have the structure where the central atom have more than 8 electron. But remember, it's acceptable. It's only happen for the element from the third row. What in the periodic table of element. Okay. I would like to share with you something happened in the literature. It's on the way to moving. Let's say when you learn for the carbon, right? You know that carbon have 4 valent electron. So if carbon make a single bond with another carbon like this, so for 4 electrons, you can make 4 sigma bond, right? And you cannot, you learn from the organic chemistry that's with the carbon. So all organic chemistry start by the structure of CH4 if you want. A carbon have 4 valent electrons, so it cannot make more than 4 sigma bond. It's something we learn in the textbook. Now, in 2017, one group in Germany, they came out with the crystal structure of this compound. You can see here, carbon, so CH3, another carbon, 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 carbon. So this carbon, you will see it have 1, 2, 3, 4, 5, 6 sigma bond. So it means what we learned from the textbook is not really helpful, if you want, to explain this case. Or in other words, as a student in the science technology, you can take like what you learn in the textbook is something very useful to explain the experimental result that already developed and available the moment the theory has been proposed. Now, with new experimental result, very likely that you need to propose, or at least you need to extend the theory to cover some new exception. For example, how we can explain one carbon have 6 sigma bond, given that carbon have only 4 valent electrons. So we are not saying that the textbook or theory, bonding theory are wrong. We are saying that we have a new experimental data. We have a new experimental evidence. We have a new discovery to say that the bonding theory that we learn, that we develop, should be further developed. And then, of course, the development of new theories should come from you guys, the future generation of the chemists. Okay? So that is my message. I want to transmit to you guys. Learn very well the textbook, understand well the limit of the theory in the textbook, and keep motivated with new discovery, with a new experimentation, and think how the theory exists in the textbook or current state of the art can be further developed. That could be the movement of the science and technology. Okay, you get what I mean? So anyone in this class can imagine how one carbon with 4 valent electrons can provide can make 6 sigma bond from only 4 valent electrons. Anyone in this class can want to imagine something, to propose something? Chi, Ting Chi, you are here?
Yeah.
Yeah, can you try?
It's not exactly sigma bond, but the bond created by blending the electron crown that created by six carbon atom. So it could use 1s2 orbital to exceed the limit.
But actually, the carbon, you know that carbon is in the second row. Is a p element. So, yeah.
But you say that there's always exception, so I just propose it.
Okay. Okay. Anyway, I don't know. It's something you may want to think about this and try to work on. Actually, this is a real single crystal structure. It's not imagination. So how the scientists from Germany in 2017 came out with this structure with this compound. So basically, you take classical aromatic compound. You do the reduction by 2 electrons in very strong acids. In previous observation, people think that when you reduce by 2 electrons, these aromatic rings will be distorted a little bit. So it changes the physical chemistry property of the product. But then they try to isolate the single crystal, and they came out with this real structure. So basically, it's not a distortion. You see that it's from C6 to become a C5 here. Okay, and one carbon moved from, let's say, from this position to top on the top of the pentagonal. So basically, it's not a simple distortion. So it's quite massive, but it's correct. It's accurate experimentation. So now people in working in a theoretical chemistry need to imagine something to explain this structure. Now, okay, so we will finish by the last topic, the strength of the covalent bond. So we talk about bond enthalpy. Bond enthalpy is the enthalpy change. So we denote at the delta S for the breaking of a particle bond in 1 mole of a gaseous substance. So for diatomic molecule, we are accurately measure quantity. For example, if you take the Cl2 gas, you cast this bonding covalent bond chlorine to become 2 atoms in the gas phase. So the enthalpy change we call the bond enthalpy. So of course, you want got a single bond and you have a double bond, you have a triple bond, you will see that the enthalpy of the single bond is much smaller than the double bond and much more smaller than the triple bond. So when you know about the bond enthalpy, we can discuss about the strength of the covalent bond. So in the case when you have the polyatomic molecule, when you have a diatomic, it's quite easy, like chloride. When you have polyatomic molecule, you take the average bond enthalpy. Let's say the case of Campbell CH4, you have 4 covalent bonds, CH totally identical. So you take the average. When you cut 4 bonds in CH4 to become carbon gas and 4 hydrogen atom gas, the enthalpy of this reaction is 1,616 kilojoule. So for calculating the bond enthalpy of one single bond carbon hydrogen, you divide by 4, assuming that the 4 bonding are identical, so they have a exactly identical bond enthalpy. Mathematical point of view is acceptable. So how we link the bond enthalpy with the strength of the covalent bond? So we can say that a molecule with a strong chemical bond generally have a less tendency to undergo the chemical change than the one with a weaker bond. So we say that you have a chemical bond with a higher enthalpy, that means you need to put more energy to break this bond. It also means this bond is more stable, and it also means this bond is more difficult to break, so it's less active, reactive, chemically active. Something more stable is less reactive. Something more reactive, that means less stable. You cannot have something stable and reactive. It's something we need to do the compromise. You cannot become someone very innovate with a lot of innovation if you are a stable guy, never want to change. So if you want to be innovative, so you have to try a lot of things. So you should be ready to change yourself. So it's quite logic, right? Easy to understand. Now, to make a calculation of the enthalpy of reaction is quite easy with the only idea, simple idea that I remember. The only thing I remember in this is that when I start from one position, from a reactant, I go to the single atom, and then the product, I'll be back to the same point here. So the total energy in this cycle, delta E, should be equal to 0, because I start from the point, I go wherever I want, but I return exactly the same point. So the potential energy should be identical. So that means the difference in terms of potential energy would be 0. By doing so, you will have the enthalpy of the reaction. That means from reactant to the product. So from the reactant, you make a single atom. And from the atom to product, you see that you go from one circle like this. Huh? So then you take the delta H, the enthalpy of reaction, it will equal to the bond enthalpy of the reactant minus bond enthalpy of the product. So if you want, here you have bond enthalpy of the reactant, and here you have a minus bond enthalpy of the product, and here you will have a minus delta H of reaction, right? So if you take delta E equal to 0, that means bond enthalpy minus of the reactant, bond enthalpy of the product minus delta S of reaction equal to 0. So from that, you remove, you take the delta S of reaction is equal to the bond enthalpy of reactant minus bond enthalpy of the product. It's very simple mathematics. It's a mathematics of the secondary school, or primary school. Very simple one. Okay. So now, for example, if you want to take the if you want to calculate the reaction enthalpy of reaction of this reaction, first you look at the which bond is broken. The bond broken will be a CH in the CH4 here, CH. So it's a reactant. The second bond should be broken will be chloride. So you have the second reaction. The product, the bond will be produced is carbon chloride, and then you have a hydrogen chloride. So from this, you can calculate the enthalpy of reaction. equal to the bond enthalpy of the reactant, so the chloride carbon hydrogen chloride, and minus the bond enthalpy of the product, carbon chloride and hydrogen chloride. So you have this, the reaction with the reaction enthalpy of 104 kilojoule per mole. So because the delta S is minus, so the reaction, whether reaction is exothermic or endothermic.
So,
So of course, it's so that's based on the enthalpy. We can say that the reaction is exothermic, right? Yeah, where it means when the reaction happens, it will release heat, and the surround temperature will be increased. So now, can you try to calculate the enthalpy of this reaction based on the data I provide in this table? Can you work on this in about, let's say, 3 minutes, please? I need to have a few minutes of rest, otherwise I feel very tired already. I mean, it's not easy. Having COVID is a very good experiment. Very tired. So, anyone got the result? Hmm? Anyone got result of this calculation? Okay, so you got the result of minus 36 kilojoule per mole, right?
Yes.
Okay, can you show your calculation? Briefly describe how you make it so that your friends can understand. So basically you have, first you look at the reactant. So you have a carbon hydrogen bond here. You have bromide here as a reactant. You have product which make Ca3 bromide. So you need to consider the carbon hydrogen, carbon bromide, this one, and then hydrogen bromide, this one. So then there is a reaction is will equal to is it correct? Hmm? Okay. So you will have 6 0 6 minus 2 4 6. Okay. So is minus 36 kilojoule per mole. Okay. Is it okay?
Yes.
Yes.
Thank you. So this is something we described already. When you move from the single bond to double bond and triple bond, the bond length will decrease and the bond strength will increase. It's quite easy to understand. Okay, here the few key points of today's class. We learn how to draw the Lewis structure. So basically, we need to put the less electronegative element in the middle, and we need to consider about the two things. One is octet rule, and the second formal charge. We describe about the resonance structure when we have two or more than two correct language structure that you can return. So basically, to be very honest, the resonance structure is quite, how to say, that's quite formal. Okay. The real one, the actual one is the experimental observation. And when you learn about the octet rule, you will have several exceptions. So at least you have three exception. You have an odd number of electron. You can have a less than 8 electron. You can have a more than 8 electron. When you have more than electron, is apply for the element from the third row of periodic table of element, because it have the d orbital. Then we learn how to calculate the how we calculate the enthalpy of reaction based on the bond enthalpy, and how we link the bond enthalpy with the strength of the chemical bond. And of course, when we talk about the strength of the chemical bond, we describe we know how about the reactivity of the chemical bond, because at the end of the thing, the role of chemistry is to make chemical reaction happen. And to make the chemical reaction happen, you need to cleavage. You need to cut one chemical bond and to build a new chemical bond. So that's why we need to discuss how one chemical bond is strong, because stronger chemical bond mean more difficult to cut. So it means more difficult to make the reaction happen. That's the way. That's the reason. At the end of the day, we need to discuss. So I think that we can end our lecture this morning here. I'm very sorry that I cannot be more like energetic, more active this morning, but hope that next week in